Hi, welcome to lecture 3. This is video 1 in lecture 3, and in today's lecture we are going to talk about whether learning is feasible or not. So essentially we are going to try to answer that question, if learning is feasible at all, and um, try to create an inference of whether we can answer that question in terms of the data, right? So we have a certain data set D, so I'm going to denote data set with a D throughout the course, right? So the data that we have is D, and are we able to infer anything outside of that? And then eventually we'll come up to something that's known as the Hovding's inequality. And this is going to stay with us like forever throughout the course because this is an essential component of something that links data set D to the question that we're trying to answer, which is mostly for something that's unknown, a data point that's new to us, right? And as machine learning practitioners, as data scientists, we are supposed to answer that question of whether the result for this new point is this versus that, right? Yes versus no, or it could be anything, right? So I just don't want to constrain it to that. Okay, so having said that, let's move on. Before even talking about this problem here, I just wanted to remind you that in the previous lecture, we talked about PLA, the perceptron learning algorithm, in which we said that we have a hypothesis set, and PLA helped us pick one of those hypotheses based on a certain criteria, right? So we talked about how to come up with that criteria in a linearly separable data set, and then eventually come down to that one hypothesis that's going to linearly separate two different classes or two different categories of data, whatever we are trying to answer, right? So that was PLA. There was this criteria that we were using. Now we are trying to establish, now we are building on that information that we already have, and we are trying to establish whether, if we are given some data, are we able to answer a question for something that's not given in the data, because that's what we're trying to get at in machine learning. For example, if you remember the credit card problem, right? I have data for certain customers and I accepted or declined their applications based on their input, based on whatever attributes I have for each of the customer. But now using that data, I don't need to answer a question for those customers again, right? What I'm trying to answer is that a new customer comes in and now I have to accept or decline the application. And that's the goal, right? That's the eventual goal. And that's why we are trying to create this relationship between the data that we have and the question that we have to answer. Because that question that we have to answer is not in my data set, right? It's outside my data set. So let's look at this like simple example. So this is a visual learning problem where we have these 6 data points, I'll call them, right? So the first 3 rows, if you can look here, right? The first 3 rows, these have like, in fact, like all 6 of them have like this training example. I would like call each of these like squares as inputs, x. This is essentially a 9-bit vector represented as a 3 by 3 black and white array, right? So that's the best way to describe this. Let's say this is my data point. This is like the first one, this is the second one, this is the third one, and so on, right? So I have 6 data points. And the inputs in the first row have f of x, like my output, or my outcome, rather, not my output, but my outcome. This is like my eventual f of x as -1, right? So the way this is given to us is that this is the when my inputs are like this, my target function is -1. When my inputs look like this, and I don't know, because this is like learning from data, so I don't have a formula for like what this is. These are just like points, right? When my input is like this, then my target function is +1. So this is a plus minus one problem. Basically, there are 2 categories, and now you get a new data point. So now this is my new point, and I want to figure out whether my f should be a +1 or a -1, right? So you can take a moment and try to decide whether your f should be a +1 or a -1 based on whatever criteria you come up with, right? My objective is to know that this is my new point that I came up with, and now I have to answer whether this is a +1 or a -1. Now, if you think about it, it's a simple learning task. I have 6 training examples here, right? So this is my D that's given to me. And then I'm trying to learn, like when this function is applied to a new input, which is this, right? New point, what should I get as an answer? Now, the chances are, if we are just looking at it and trying to decide that, it depends on your criteria, right? So most of you will come, like many of you will come up with +1, many of you will come up with -1, right? And both are valid, because if you look at this output, this outcome, and let's say the criteria for picking up, or the criteria for deciding what this f is going to be, is that the leftmost square is a black square always, right? So the topmost left square is a black square always. That fits in here. So that kind of tells me that my f is essentially going to be -1. Now, if you picked your criteria as some kind of a symmetry in this like array of 3 by 3 like vector, right, or bits, or whatever you want to call them, right? So if we are thinking of the symmetry, then you can see that there is some kind of symmetry that exists in this data point, right, the fourth data point, and then this one as well, right? So it is symmetric in a certain way, right? And this one is also symmetric in a certain way, right? So if symmetry is your criteria, then you can come up with saying that my f is +1, right? And both are valid answers to this question, right? It could be +1 and -1. So basically the information that I have, or the data that I have, is not sufficient. It's not enough to answer this question of whether the outcome is a +1 or a -1. So now this raises a question about the feasibility of learning, right? Because we have some data, we use it, and we try to answer the question outside that data. And so we need to understand, is learning feasible at all or not, right? Because this dilemma is not just restricted to this. This was a simple problem. It might go on for like more complex situations. And that's what we're getting at, right? So does this mean that learning from data is not possible? Is it doomed? Well, a short answer to this question is of course not. That's why we are here in this course. And so there is a possibility, and when like we can say something about like outside the data as well. So let's see, how can we say something outside the data? Okay, so moving on. In order to establish this relationship between inside the data and outside the data, we're looking at a very simple bin model. Again, this is given in the book, but I'm going to elaborate a little more here. What we are trying to draw an analogy of here is that we have this larger population. Think of we have this entire population of a country where elections are coming up, and you're trying to predict which is the candidate who's going to win. And so you cannot go and survey like the entire population, but you can do that for a small number of people. So that's essentially a sample, right? So based on that sample, you can decide whether you can come up at least with the information that this sample, at least this subgroup of people, will vote for this, or the probability of people voting for in that sample is this much, right? So that's what we are trying to draw an analogy of. So here we have a bin, which is this like universe. So this is all the data that we have, right? So this is the universal. Consider this bin as like a universe of red and green marbles. So it has like infinitely many red and green marbles. We don't know how many, okay? And the proportion of red and in green marbles in the bin will always be such that we can pick a marble at random, and the probability that it will be red is denoted by mu. Right, so mu is the probability to pick a red marble. Obviously 1 minus mu is the probability of picking a green marble, because we have only those two of them in this entire universe. Now, an important assumption here is that mu will always be unknown, because this is about the population as a whole, which goes back to the polling example. You know the sample output, but you don't know what's happening in the entire population and what is the outcome going to be. Right, so this is what's happening here. Now we picked a sample of like 10 marbles randomly, right, with replacement, or in general, let's say any n marbles from this bin, and we can observe the fraction of red marbles in my sample, right? I know how many red marbles are there in the sample, and based on that I can calculate the fraction of red marbles in this entire sample. For example, I have like a total of 10, and I can see there are 3 red marbles, so this fraction is 0.3, right? So I know something about mu, right? But does this value of nu, I don't know, I'm sounding really like mixed up. So this is nu and this is a mu with an m, right? So this is mu and this is nu. Okay, so does this value of nu help us in any way in answering the question of what is the value of mu? Well, one answer to that question could be that regardless of the color of like the red marbles that I picked in my sample of size 10, right? We still don't know the color of any marble that we did not pick from my bin, right? Which kind of tells me that it is totally possible, right? That this has a high value of mu, which means the probability of having a red marble in there, let's say it's like really high, it's 0.9, but it's totally possible that I did not pick a single red one and I picked all the green ones. So essentially my nu came out to be 0, right? It's totally possible, right? Just by looking at the bin, I can tell that it is like one of those situations that can come up, right? But we're really interested in knowing mu, right? And just by like think about it as in terms of the larger picture, this is a really simple problem, and other machine learning problems could be like determining a function, not just like finding a fraction of this red marble in a bin. So basically, using this approach or this setup, what we are trying to infer is that whether my nu is equal to mu, or can it get equal to mu or not, almost equal to mu or not, right? Well, again, the answer to the question is we cannot be sure. It is possible because, as I said, mu can be like almost 1, right? Mu can be almost 1 and nu could be 0, right? But it is probable, right? So it is possible to get this. What I mean to say is it is possible to get this one bad case, but it's not probable, right? So basically what we're trying to say is that this is a possibility amongst the lots of possibility that we can realize, right? But it is not probable. Okay, so basically probability comes into picture and probability comes to our rescue when we are stuck at this situation whether nu comes close to mu. Although we cannot like conclude this with like 100%, like this conclusion being 100% correct, it's not possible to make any conclusion about nu, but it is probable, as I said. So how does like probability fits into this entire question, the entire equation, and how does probability help us resolve this dilemma? Okay, so let me draw a picture here to show you how probability comes into our rescue. Let's say I have this like experiment where I'm drawing 1000 marbles. I draw 1000 marbles repeatedly, right? So marbles repeatedly, right? And what I do is I plot the outcome for the nu on a graph, right? So let's say I have like this graph, which I'm really bad at drawing, and mu is 0.4. Let's assume that my mu is 0.4, so it lies somewhere here, right? My mu is 0.4, and what I do is as I keep drawing these 1000 marbles, I will keep calculating my nu, which was, remember, the fraction of red marbles in my 1000 marbles, right? So let's say in my very first draw, I found my nu came out somewhere here, right? And let's denote it by this star, right? And then in the next draw, it came out to be somewhere here. In the next draw, it came out to be somewhere here, and then here, because it's, of course, like possible to get all values in this entire spectrum from 0 to 1, but most of the times we'll get a nu, and if you like write a program and do this experiment, you'll find that most of the time we'll get a nu that's like really close to mu, right? So basically we will get more values around here and maybe 1 or 2 values here, but less number of values depending on like how many times you're repeating the experiment. And this will go on and on, and let's say we did quite a number of these experiments, right, drawing this and calculating nu. What I'm going to get is somewhat this kind of a picture, right, this kind of a graph, and I'm sure most of you are familiar with this, the binomial that represents this outcome, right? Binomial almost Gaussian, I would write, right? Okay, so what do we want here? What do we want? We really want nu to be as close to mu, right? So we are getting a lot of nu's close to mu, right? This was my mu, I would write. 0.4, and especially if we kind of restrict this in this region, right, we'll see that nu is very close to mu. So this region could be our tolerance level, right? In my experiment, I define something known as tolerance, and let me denote it by epsilon. And this tolerance is going to be something that's an input from my side, and I'm not tolerating any of the new values outside this range, right? Because everything outside this range is something that we're not interested in, because I really want this to happen, right? And so this is, I'm calling it bad because I don't like this, right? It's just like outside the range, the nu and the mu are really further apart. So I don't really like this part, but I really like this part. And I have defined that tolerance to be epsilon, right? And so all the mu's that lie within this like tolerance level will be something that I'm interested in, right? So these are the good ones. And what I want here is like the bad outcome here is if I find the difference between nu and mu, and if it is greater than my tolerance, right, then this is something bad. This is my bad outcome, right? So my good outcome is the opposite of this, obviously. Now you can tell. So my good outcome is okay, let me write it again. Nu minus mu being less than or at most equal to my epsilon, right? Because you can tell that this is my tolerance range. So this is essentially my mu plus epsilon, and this is my mu minus epsilon, right? This entire range, right? And I want my nu to lie somewhere here, right? So this is my good outcome. This is what I'm trying to get at. Basically, this graph depicts, this is something that it depicts, bad, let me make it, emphasize it, bad is possible, as you can see, of course, and that's what we said, right? I could have drawn like a sample of all green marbles, right? So that was a possibility, but good is probable, right? There is a higher chance, a higher probability of getting the good outcome, which is when nu minus mu is less than that tolerance level epsilon, which obviously I'm going to decide. But what we're getting at by looking at this experiment itself is that as the size of n grows, this was my n, the sample size, right? So as n grows, right, as the sample size becomes big, then nu tends to be closer to mu, right? So this is my result out of this experiment, that my nu becomes closer to mu. So this is what I'm trying to get at, right? So there is a possibility that I'll not get nu any close to mu, but good is probable. So this thing is possible, probable. And that's how probability comes into our rescue, right? So I would just like pause here and jump into the next video where we will start talking about quantifying this relationship, basically trying to establish the relationship between nu and mu by using a bound that's known as the Hoeffding's bound. So see you in the next video. Thank you.